The model with the center still fails by 15 degrees, so we cannot use that to measure the position of a planet. What is wrong with this model, in fact, is that even though you can reproduce with some reasonable accuracy the shape of the orbit, the velocity of the planet in it is wrong. So this model assumed that the velocity of Mars is uniform. To improve on the model, we somehow have to include the non-uniform motion. How do we include the non-uniform motion in a circle? That was the next degree of sophistication in the model of the ancients. To fit the velocity of Mars, Ptolemy added a third device, which is called the Equant point. So the Equant point is defined as a point about which the angular velocity of a body on its orbit is constant. So the idea is that the body is not going in uniform motion in its orbit. Seen from the sun, the motion is not uniform. Seen from the center of the orbit, the motion is not uniform, but there is a point, this point here, the equant, that if you were an observer at this point, you would observe the planet going in uniform motion. So from this point here, the equant, you can measure equal angles at equal times. So about this point, the equant, you can define the angle to the planet as being the mean anomaly. About this point here, the angle that connects the planet to this point is going to be doing uniform motion. And then you can write that the mean anomaly is equal to the orbital frequency times the time. It's a geometrical way to interpret the mean anomaly. It's an angle. So there are three angles in the Ptolemaic model: true anomaly, eccentric anomaly, and mean anomaly. Notice also why the eccentric anomaly was defined in this way from the center of the orbit. In the elliptical orbit, you have to define the circumscribed circle, which is not where the planet is, but if the orbit is a circle, both the true anomaly and the eccentric anomaly meet at the planet, and so does the mean anomaly. So the three angles meet at the planet, only their origins are different. For the true anomaly, that's the sun. For the eccentric anomaly, it's the center of the orbit. And for the mean anomaly, it's the equant point. So if you define the equant in this way, you can write the position of the planet with respect to the sun as x is equal to a times the cosine of the eccentric anomaly minus the position AE, which is the eccentric distance of the sun. As for y, it's just a times the sine of the eccentric anomaly. And the mean anomaly is omega times time. To find the relationship between mean anomaly and eccentric anomaly, you consider the triangle LCP. This angle here at vertex L is the mean anomaly. The external angle with vertex on C is the eccentric anomaly, so the internal angle is 180 minus the eccentric anomaly. Therefore, the angle centered on the planet is the mean anomaly minus the eccentric anomaly. This side here from the center to the planet is A, and this side from the equant to the center is A times the eccentricity. Applying the law of sines to this, you find sine of m minus e over AE is equal to the sine of m over A. You cut the a's, take the arc sine in both sides, then you can solve for the eccentric anomaly. So there you have it. The eccentric anomaly is the mean anomaly minus the arcsine of the eccentricity times the sine of the mean anomaly. If you measure the mean anomaly and you know the eccentricity, you immediately have the eccentric anomaly. And with that, you have x and y of the planet. So these are the steps on the Equant model to find the position of the planet. Measure the time. Having the time, omega t gives you the mean anomaly. Having the mean anomaly, you calculate the eccentric anomaly. And from the eccentric anomaly, the position of the planet. So let's see how this fares against the observation. This is in the heliocentric view, the Equant model against the orbit of Mars, and the geocentric view. Not only you reproduce the shape of the orbit, you reproduce also the velocity of the planet. To what accuracy? You reproduce it here, the longitude of the planet, to about 30 arc minutes. Remember that the precision of the ancients was a degree. If you can reproduce the position of a planet up to 30 arc minutes, you have a very good agreement between the observation and the model. So you accept the model. This is how this model compares to the observation of any planet. Mercury, Venus, Mars, Jupiter, and Saturn, the planets that were seen by the ancients. So you can see that even for the highest eccentricity, which is the eccentricity of Mercury, the Equant reproduces the observation to within a degree accuracy. Mars goes to about 20 arc minutes, and for the other planets is even less. This graph here shows the astrometric accuracy during 2,000 years. So in the y-axis, accuracy in second of arc, and the x-axis is the time. The ancients had accuracy to about 1 degree. So if you have a 30 minutes error, that's pretty good. Now, as time passes, accuracy started to increase and increase until it got to the time of Tycho that did observations accurate to 2 arc minutes. Suddenly, you cannot accept 30 minutes errors anymore. The Equant model started to not really reproduce the observations, so it had to be discarded.